I'd like to tell you about a project which began 3 years ago in Durham, in which we've been analysing medieval pigments. And the trade name for the team is Team Pigment, and so I'm the guy who gets to represent the hard work of the other members of the group. This began when the Lindisfarne Gospels exhibition pitched up in Durham. As you may have heard yesterday when Sarah was talking, the Lindisfarne Gospels were brought to Durham and an exhibition was put on in which several or many manuscripts that were produced in the northeast came to the Palace Green Library in Durham next to the cathedral, and we were asked by one of our chemistry alumni if we could analyse the pigments on the manuscripts without touching them, without any damage, because as a chemist that was a challenge, and I said yeah, we could do that. That's no problem at all. The criteria were that the analysis must be non-contact, non-damaging, and leave no mark on the page, to cause no footprint, if you like, on the page. And I suggested that what we could use is a technique known as spectroscopy, in particular Raman Spectroscopy and Diffuse Reflectance Spectroscopy. And in my laboratory I've got a Raman spectrometer, so yeah, bring a book on over and we can have a look at it. I said, no, you don't understand. And my colleagues in history discreetly and kindly explained to me that you simply don't move manuscripts around in this way. I didn't know that. In chemistry we use handling samples that we can move anywhere in the world. And so I had to learn the language of my colleagues in history and within the cathedral and the university library. So I said, okay, well, what we could do is we could move our spectrometer to your books. It's not a small undertaking, but we can do that. Because clearly the books are priceless, which I now realise. We cannot move the books to the machine, we move the machine to the books. Because of this change in sort of in operation, many books, in particular the books in the Durham Cathedral collection and the Durham University collection, they've never been examined in this way. In fact, most manuscripts that you have sitting in archives will never have been examined using scientific forensic techniques, simply because the logistics of moving the book to a spectrometer is prohibitively expensive and dangerous, because chemistry departments always burn down, as everyone knows, they're dangerous places. And scientists generally are so reluctant to move their equipment because of the momentum of doing that, that the two never meet. So we decided we'd take the equipment to the books. For the next 3 slides, what I want to show you is the techniques that we use. And I'll explain these hopefully in a simple way. The first technique I mentioned was Raman Spectroscopy. And I want to reassure you that this is a technique that's very safe and is very useful in analysing, diagnosing the materials on the page. This technique is going to tell us about the molecules which the pigment is made of. Because molecules are a bit like naughty children, they're always jiggling around. They jiggle around at a particular frequency, a particular speed. And we can measure that, we can measure the fingerprint of the material, because it's unique to that particular material, we can work out what the material is. And so we simply shine a laser beam onto the page. Now at this point you're thinking, gosh, a laser beam, that sounds a bit dangerous. And I'm going to step away from the microphone here for 1 second, I apologise. Here's our laser coming in, here's the light scattered. When a laser beam hits an object, so for example, if you look at the laser spot here on the wall or on my hand, what is happening is the laser beam, the light, is shining off my skin and it's scattering back to your eyes. And what you're seeing, 99.999% of the light you're seeing coming from that point is exactly the same colour as the light produced by the laser. So that's represented on the screen here by the green lines. A tiny, tiny fraction bounces off with a different colour, a different wavelength as we refer to it. And by looking at the difference between what came in and what went out, that tells us about the molecule vibrating. So all we have to do is shine a laser beam onto the page and that will give us the Raman spectrum. Now you're probably thinking, laser beams, they're dangerous. They're going to burn holes in our books. And that's exactly the response we get from virtually every librarian we've spoken to. You know, you're going to shine a laser beam onto the page? Are you mad? Everyone thinks of this chap here when they think laser beam, but that's absolutely far from the truth. The laser beam that we use is actually no more powerful than the laser pointer I have here in my hand. We're very aware of the risks. I work in laser spectroscopy. I've done that for the last 30 or so years. I'm very well aware of the risks posed by laser beams, and we know exactly what we're doing. We have got it under control. Just to show you a typical Raman spectrum or Raman spectrum, this is an example here in the box, and the position of those lines, excuse me, and the intensity of those lines tells you the fingerprint of the material. So the top trace is that of arsenic 3 sulfide, orpiment, the bottom trace is red lead, which are common pigments that you'll find in manuscripts. The next technique I want to tell you about, excuse me, is diffuse reflectance spectroscopy, sometimes referred to as FORS by those in the trade. And diffuse reflectance is quite a straightforward technique. In fact, you're doing diffuse reflectance spectroscopy all the time you're looking at me or the material around you. The white light from a light source shines onto the object. Colours that aren't absorbed are reflected, they're analysed by our spectrometer, and by looking again at the difference between what goes in and what goes out, we can analyse the spectrum and therefore the material on the page. So it's simply shining a light onto the page and looking at the light that is scattered from the page. And we can do that both point by point, or we can do it by imaging. And this perhaps is close to home. Here we are taking an image through a filter of the page. Except in our case, instead of using a simple RGB camera, such as the type used by the lady at the back there, where you take an RGB image that builds up a nice photograph that you can visualise, you can see, excuse me, we take photographs at specific wavelengths, not just in the visible portion of the spectrum, but also in the ultraviolet and the infrared spectral regions. And from those, we can process them with a computer, we can generate a whole lot more data. And I'll show you some examples of that later on in the talk. I mentioned the problem of moving our spectrometer. We had to move the mountain to the books. In fact, in this case, we've got three hefty guys here moving a part of the spectrometer. In total, it weighs about 1/3 to 1/2 of a tonne, depending on which bits we've got attached to it. The lower picture shows the equipment in situ being fettled by a couple of engineers. This equipment takes a week to move, not just the physical lifting of the equipment. It's a bit like a Formula One racing car. To get it absolutely spot on, to get it working perfectly, you have to fettle it, you have to tune it, you have to make sure it's relaxed in its new environment, it has to adjust to the climate, and so on and so forth. This is a major undertaking. So when we did this first project 3 years ago, it took us a week to move the spectrometer. It stayed in situ in the library for 6 months while we were doing measurements, and then it came back out again. We lost the use of the spectrometer in the Department of Chemistry for that period. And it cost us, well actually it cost us nothing because the company who made the spectrometer did it for free. But had we paid for it, it would have cost us about £10,000 simply to move the machine over. However, when it's in place, it's fantastic. Here we are analysing a manuscript. This is one of the Durham Gospels, an 8th century manuscript. You can see here what we have, and again, I'm going to have to point with my finger, I think is the safest. We have a microscope focusing the laser beam onto the page, and the book is held on a cushion. It's nice in a comfortable, relaxed position. I should say that the rosary here was placed by Liz, not by us, because I noticed there's one of the cathedral staff here in the audience. We didn't do that. We normally put it off the writing. And the book is moved across the ways to bring the right region into focus on the page. We can analyse a spot about a micron across. That's 1/1000 of a millimetre diameter. That's the size of the spot we're analysing. I mentioned about the laser power. When I take a laser beam, such as the laser pointer here, that spot is about 1/2 milliwatt of energy. That's telling us the laser power. And that's the same power that we're using in this case down the microscope. The difference being we focus the laser beam to a small diameter. So in effect, the laser beam is more intense on the page, but we know the damage thresholds for pigments on the page. We know we're well under the threshold at which damage will occur. And in fact, if we compare our laser powers to that used by previous workers in the field, we're about 1/10 or 100th of the power used by other people. And that's because advances in instrumentation have allowed us to do that. So we are safe, we're not causing any damage. And I'm happy to discuss later on with people if they want to know how we know that, we can explain, we can show that evidence. This is a real pain though. This equipment is great in Durham. I can move from one side of Durham City to the other with my kit, that's easy. But I couldn't bring that on the train here with me to do an experiment in front of you live today. Not that I have done, I shouldn't have had, but we could have done. What we wanted was Raman Spectroscopy in a suitcase. And as a scientist, I'm interested in building equipment to do new things, so we built our own spectrometer that does everything that that large spectrometer does, but fits into a small suitcase. In fact, that suitcase there, this is a small packing case, it's on wheels, and we can pack this up either in my car, on the left-hand side here, or we can carry it on the train or planes or whatever, and we can set it up in half an hour of arriving at a library we can be working. So it's a really mobile piece of equipment, but it has the sensitivity and performance of the larger equipment. And that allows us to go mobile. In fact, on the bottom right there, you can see Richard Gameson, my colleague, working in the Corpus Christi Library in Cambridge, where we're looking at one of the manuscripts in their collection. So we can go on these campaigns visiting other libraries to look at manuscripts, and we'll see why that's important in a second. However, I'm sure you'd like to see some beautiful manuscripts. This is a book that belongs to Durham Cathedral Library, A210, 7th century Gospel book fragment. And this was particularly interesting to us. We're interested in identifying the pigments on the page and working out what they're made of and ideally where they've come from. That was the essence of our project. I always point out at this point, that hole there, that wasn't our laser beam. That was an animal tick or an injury or whatever to the calf that this was made from. So that wasn't us. We don't burn holes in books. We are extremely cautious, extremely careful. Again, if you grab me over coffee, we can tell you some stories about that. The data we're going to get from this page are these Raman spectra, and they're forensic identifications of the pigments on the page. So as we look here on the top trace, the yellow in this illumination gives me this characteristic spectrum. That's the highly poisonous arsenic sulfide that is characteristic of insular Gospels. It's used widely and lavishly throughout the insular period, probably come from southern Italy, and it gives us a spectrum that is absolutely unequivocal, it's unique, and it sticks out like a sore thumb. So the yellows on the page are arsenic sulfide. The reds and oranges on here are red lead. And we'll look at this spectrum in a second. Remember that red trace here. Remember the pattern there, the number of peaks and their relative intensities. The red lead, well, that's a pigment, again, we find in this period. We find that in virtually all of the insular Gospels that we've looked at, and we've looked at quite a few now. The blues in this case, now there aren't many. When you look at the insular Gospels, what we've found is that there are some with blues and there are some without. And the blues tend to be indigo. This is a naturally sourced blue pigment. Again, happy to chat to people over coffee about whys and wherefores of indigo. And the green on this page, or how do you make green paint at school? You mix your blue and your yellow paint in various proportions to give you shades of green. It's exactly what the artist has done here. They've mixed the blue indigo and yellow orpiment. You can see there are peaks due to indigo in this trace, and there are also peaks due to orpiment in this trace. So we know that the green on this page is a mixture of indigo and orpiment. It's a mixture which is referred to as Virgo. There are other materials that can be green, copper-based greens, for example, and we'll see that in a couple of examples later on. Copper-based greens, which are derived from the degradation of copper metal, they also produce nice green on the page, and we have examples of those. They don't give a Raman spectrum that is the same as this, so it's easy to differentiate between the two. So remember that spectrum of red lead. Here's another book. This is one of the, again, another of the Durham Cathedral manuscripts. This is A216. And on this illumination, at the bottom right here, we have this dragon or hound's head, which is filled in. It's about the size of a small fingernail, and it's filled in this beautiful orange-red lead. It's slightly degraded, but it's in very good condition, really. We've done about 50 measurements on that head, and every point, every time we take a spectrum from a different point on that dragon's head, we get the same spectrum, which is represented on the bottom there by one example. It's always pure red lead. However, farther up the page, just up here, we have a scribal mark drawn in, again in red lead, and we go off and analyse that. And depending on where we are on that scribal mark, we get different spectra. We either get the spectrum of red lead, this trace here, or we find another red or orange pigment called massico, which is another lead oxide. That tells us that this is a different batch of ink, and this is very interesting. It's perhaps not surprising it's a different batch of ink. The scribe and the illuminator, of course, may be different people, done at different times. But it tells us that the chemistry of those two pigments are different. In fact, when you make red lead, one of the ways of making it is you roast white lead, and you roast it up to quite a high temperature under very carefully controlled conditions. If you overcook it, your red lead degrades to a mixture of massico and red lead. So the guy who made the top batch of ink, this batch of ink here, he'd overcooked it. He wasn't as well trained, he wasn't as experienced or as good a chemist as the guy who made, and I refer to these scribes as chemists because this is really hard chemistry to do. Not in a laboratory, but if you're doing this in your backyard, this was done on Lindisfarne or in Wearmouth or Jarrow, to do it in your backyard at home, this chemistry actually was very difficult. And so hats off to these guys. They were extremely good scientists, the scribes who were producing these inks. Let's have a look at another example of an insular gospel. This is one of the corpus manuscripts, 197B. And this manuscript, the reason I've shown this here, excuse me, it's for two reasons. First of all, it's a fantastic image of an eagle. The reds on here are red lead, the yellows are orpiment, and in fact the coppers on this page are copper-based. The greens on this page are copper-based pigment. And we know that from the diffuse reflectance spectroscopy and the lack of a Raman spectrum. And what we decided to do here was play some games. We decided to take some images of this eagle in the infrared, this image here, and also in the visible. This is one of the green images. And if we take these two images and divide, in this case, the red by the infrared, this trace here, we get the Andy Warhol version of the Corpus 197B. But actually what this tells us is anything yellow on the page there, we've produced a false colour image of course, anything yellow there is copper-based pigment. In the image bottom right, I've taken the red image divided by the green image, and anything that is yellow on that page is actually red lead. This is allowing us to map at a page at a time the pigments on the page. That's giving us quite a useful measure of pigment use, or at least a first stab at what pigments are being used there on the page. The Raman spectrum, remember, is a micron or so diameter spot, and it's giving us a spectrum every minute or so. To scan a whole page with a Raman spectrometer would take years, literally years of our time, and the book wouldn't stay still for long enough to do it accurately anyway. These data took about 1/60th of a second per shot, so it's less than a second's work to process and visualize this data. So quickly, excuse me, just remind you of these pigments we've found. We see red lead from lead ore. We've found orpiment, which is the arsenic sulfide, which has been imported probably from Italy. The verdigris, this is actually showing that copper can be degraded quite nicely by urine to give you verdigris. And on the bottom right there is a woad plant, which grows like a weed in the northeast. So we looked at these books that had been put into the exhibition in Durham, and then we went on and thought, well, what about some of the later books? Let's look at the books from, say, 1066, and the post-Norman books. And this is an example which belongs to the Durham University. This is a book, the Book of Simeon. And what we found here were different pigments. We're finding instead of being red lead, we've got vermilion, mercury sulfide. Instead of being indigo, we've got lapis lazuli appearing. And so this raises a question then as to how pigment change has occurred over the years with societal change and with changes in the technology of book production. So the project, after being an initial, can you look at a few books, has emerged into a much more complex program now, looking at how pigment use and how pigment technology is developed across Britain through the ages. And for that we need access to manuscripts through the ages, well-provenanced and well-known manuscripts. What I'd like to skip on to, excuse me, quickly, is an example of how we can now use our multi-spectral imaging to do this. This is a manuscript in the Bodleian Library. It's a map book from the 13th century. And on the right-hand side of the image there is a 15th century map. It appears in the book. It's not a palimpsest. It's an original folio in the manuscript. And we were asked, are the pigments in that the same as the pigments elsewhere in the book? Clearly, it's got more information than it should have there. We've analysed this using Raman Spectroscopy. We know exactly what the pigments are. What I want to show you is some of the multispectral data from this and how we can treat that multispectral data to give us pigment maps. Here we've recorded 5 images from the blue through to the near infrared. Again, each image takes a 60th of a second to acquire. And then we can do a mathematical procedure called principal components analysis using these data, and we can generate maps of the pigments on the page. So, for example, after literally a couple of seconds thinking, the computer will tell us these pixels on the page all have the common feature which is associated with lapis lazuli. The next one is the copper-based green system, the next is the orpiment. So within a snap of the camera shutter, we've got data that we can use for the scientific analysis of the manuscript, not just the production of a nice picture. And so what I would urge you as digitizers of manuscripts, forget about the nice RGB cameras, the Canons and Nikon cameras. What you should be doing is acquiring spectrally relevant data that can be used for other purposes. From these images, or from the images, these images here, I can give you a nice picture, a nice colour photograph. I can regenerate the original photograph, the original image. But from these data, I can also do some science and tell you what the page is made of. And I think that must be the way forward. When you're taking photographs, please just think of the scientist, get an ultraviolet image, get an infrared image. We can reprocess that data quite readily then to do other things. The final thing I'd like to say is that we have a problem. We have lots of data. We need to archive this data. We need to bring this data together with the images, the photographs of the manuscripts as well. One of the examples, this is an example of the Goff map from the Bodleian Library, where we're putting our data onto an image of the map, and each point that you'll see on there has associated with it hyperspectral data, it has images, it has, or microscope images, it has Raman spectra and so on and so forth. And this platform is freely available. We'd also like to incorporate this with more sophisticated packages so that you can interactively process and analyse the data. And in fact, one of the final topics that my colleague Richard Higgins will talk about is the Durham Priory project and how we can interact with that to make our data accessible beyond the pigment work. So what I'll quickly do, I'll flash over, I realise time's getting on. I'd like to say thank you very much to the colleagues, the collaborators, and particularly the librarians who've trusted a bunch of scientists with their priceless manuscripts. These are the guys who have actually done the work. You know, it's always the boss who gets the money who has to stand up at the front and talk. We were funded quite generously by one of our alumni and by industry, so the people who make spectrometers have been very generous in giving us time. And the libraries on the right here have very generously granted us access to their medieval manuscripts. We've looked at about 100 or so now, and thank you for your attention. Thank you.